We will be solving the following problem. It's a simply supported beam. We will be designing it using LIFD. The loading that we will be using is shown here. We have a distributed load and a concentrated load. The beam weight is not included. That will be taken into account using RISA. Also, lateral supports are only provided at the points indicated here. The steps we're going to take in order to solve this using RISA are as follows. We will need to set global parameters. This includes the appropriate code and a solution. Then we will have to check consistent units, modify the grid in order to create the model, and in the process of creating the model, we will have to set some preliminary section properties as well as appropriate material. The lateral supports will be set here. This is a little different than what we've done in previous videos. Then we'll set appropriate boundary conditions. Finally, we will input the loading. Here we will include the weight of the beam. The last item is do load combinations and perform the solution. In the solution, we will ask RISA to conduct the appropriate optimization. Once we have RISA running, one of the things we need to do is set global parameters. I'll give it a title, example. And then we'll go to codes. And in codes, we're going to use the LRFD code, the 2010 AISC 14th edition. Also here, we need to adjust the stiffness. This will be used later when we look at the direct stiffness method. And then the solution said we're not going to do anything with that. That's okay. So we'll apply this. Okay, this. Our units, they are US customary, so they're consistent. We'll move on and modify the grid. The grid, we have 9-foot spacing, so we'll have 4 spaces at 9 feet in the X direction and 1 space along the Y direction. This will give us a grid like so. Now when we create the members, we create the model, we need to make sure that we have the appropriate lateral support or the unsupported length. And one way to do that is by going to the modify design, and in L comp, the bending, the top portion of the compressive flange has to be unsupported. So I'm going to call this segment. And this, what that's going to do is going to allow RISA to specify the entire length of the member as the unsupported length. We'll do that in case we have negative bending. We'll do that to the bottom as well. And then we'll go to the members. We'll set just a member, any old member here. 8 by 10 is fine. We have a beam, wide flange. So this is our section set. We're not going to modify it. Typically you would if you had a large model, but this case is relatively small. Make sure the material is A992 for the W shapes. And then we go ahead and create our members by clicking like we've done in the past. We're going to create the members the same length as the unsupported length. So we got 2 9-foot segments and an 18-foot segment. Next, we have to do the supporting conditions, and we got pin support at one end. Again, we got to make sure that this doesn't translate out of the plane to dimensional plane, so we'll fix that. And then we do this for the roller support as well, and the roller support is going to be allowed to move in the X direction. There we go. And now we create our loads. So in the basic load case, this is different than what we've done in the past. We'll have a dead, and that's going to be category dead load. Here, I'm going to put negative 1.2 to include the beam of the weight and the load combinations. Then we have live, and this we don't have to do anything. So we have created our 2 basic load cases. So anyway, we now go ahead and apply our loads. We are going to do the negative or the dead load first, and that was 3.5 kips per foot, and that's dead. And we'll apply it to the first, only the half of the span. And then we go and do the live. The live was 1 kip per foot, and we'll make sure that that's live. And we also have the 30 kip concentrated load, so we'll have to put that in as live and negative 30. We'll apply that to the mid span. Now we have the loading. We have to create our load combinations. Our load combinations, we're going to generate those using ASE 7 2010 strength. That'll be compatible with the LRFD specifications of AISC. And so we don't have any rain load, snow load, or roof live load, so we'll generate this. And notice only 2 load combinations. That's okay. At this point, we're ready to solve the problem, and so we'll solve it. We'll do an envelope. That way it will solve both of the load combinations and give us the worst case. And so we end up with this as our solution. Let's check out the moment diagram. And the moment diagram, apply the magnitude. Let's go 100%. Apply. It looks like 687 here and about 900 and some odd here. We'll see that in a minute. So the next thing is we want to check our suggested design. So there's suggested design right here. So RISA has decided that a 27 by 84 would be the most optimal. So we can also change this guy here to make sure that the whole beam is a 27 by 84. So anyway, we'll right click and solve again using the suggested shapes. And in the suggested shapes, we don't want to carry anything with masonry or wood walls. So we'll do this and notice now it's coming back with a 30 by 90. Oh, great. Let us solve again. This is because we included the weight of the beam, so it had to go up a little higher. And so we solve it again, and we click OK, and this time we don't get any changes. We can also check the capacities by going to design results, and in design results the design results are shown here. So we have a 30 by 90. Notice the moment capacity check. So this is the ratio of the available capacity to the required strength. Notice here is the unsupported lengths, 9 foot and 18 foot. The shear capacity, the ratio of the shear capacity to the available capacity to the required capacity is quite low. And here's the moment capacity of our section, 1061. And then notice the CB factors. It also computes the CB factor. CB is 1.52 for the first segment. The middle is about 1. And then the second, or the longer segment, is 1.65. The reason this is not 1.67 for a triangle is because we have the beam weight. So how does this compare to the code checks? Well, here's RISA moment. We have the maximum moment is about 923. This includes the beam weight. Remember, we went and did a suggested shapes. This was solved a little bit differently with a W18 by 119 to start with, but we still ended up with the same sections, 30 by 90. The steel code checks, we still have about 1.519 CB and 1.656 CB for the 18-foot segment. Our capacity is still the same. Here I went back and I changed the entire beam, all 3 segments, to be the exact same shape, W30 by 90. Great, hope this was helpful.